video, we're going to cover Chapter 8, which is the wave-particle nature of light. And this is going to lead into electron configuration in Chapter 9. So first off, light is a form of electromagnetic radiation, so EM radiation, and it has wave and particle properties. So that's everything from visible light to gamma rays, radio waves, and we'll talk about the spectra in a minute. And all light in a vacuum has a constant speed of c, what we call 3 times 10 to the 8 meters per second. And this is not -3, this is just a dash. So 3 times 10 to the 8 meters per second is the speed of light of a vacuum. And light has wave and particle properties, meaning waves, such as sound waves, they can propagate in a wave-like manner. Particles work like particles, such as if you throw a marble across a room, it's going to follow a parabolic pathway because of gravity. But light does not have mass, so photons do not have mass, so their particle nature is not like our normal mechanical models that we see of particles that have mass, but they will move in straight lines. Light has particle-like properties and wave-like properties that we'll talk about. So one of the wave-like properties, or a few of the wave-like properties, are amplitude, frequency, and wavelength. Now the amplitude is the height of the wave, and if we're referring to light, this is how bright a light is. The wavelength is the measure of the distance covered by wave, so this is usually in meters, and it can be in nanometers if we're talking about the visible light spectrum, where it goes from violet, which is around 300 to 400 nanometers, all the way to a red light, which is around 700 to 800 nanometers. And we have our frequency, which is V. Here's V, but this is actually the lowercase letter, Greek letter nu, which is the measure of how many waves per second. So 1 over S, or this is also called hertz. And I'm sure you're familiar with megahertz, gigahertz, etc. So here's a wave. You have amplitude is the height from the baseline. Wavelength is peak to peak or trough to trough. And the frequency is the number of waves that pass through a point in a given time. So there is a relationship between the two. They are inverses. Wavelength and frequency are inversely proportional of one another. So if you were to multiply, based on this equation, multiply wavelength times frequency, you get the speed of light. And you can go from one to the other very quickly. If one question gives you wavelength in meters, you can then convert that into frequency using this equation. So here's an idea of different wavelengths and frequencies. So different wavelengths and frequencies correspond to the different colors. So in our spectrum, and also the different types of radiation. But if we're just going to talk about something that we're all familiar with, which is the visible light spectrum, we can see that different wavelengths and frequencies correspond to different colors. High frequency, meaning a higher frequency number, more waves per second, is a indigo, blue, and violet color. And then a longer wavelength, or a lower frequency, is going to be a red color. And in the middle, you have yellow and green. And this spectrum is Roy G. Biv. So red, orange, yellow, green, blue, indigo, violet. Roy G. Biv. So this is in order of increasing energy. Energy is something we'll see in a minute, is proportional to the frequency. Higher frequency means higher energy. And it also means more deadly, because if you have violet, what comes after that? Ultraviolet in the energy spectrum. So ultraviolet is higher energy than violet, and we know ultraviolet comes from the sun, and it can give you cancer if you are exposed long enough. So we have Roy G. Biv from increasing energy, meaning increasing frequency, and also decreasing wavelength, because we know that frequency and wavelength are inversely proportional. So here is the entire EM spectra and we have starting from lower energy to high energy, or lower frequency to higher frequency. And it's good that you memorize the sequence, not necessarily the values, but the sequence. So radio waves are the lowest energy. You have microwaves, infrared, then you have the visible light spectra, which is what we see, a very small percentage of the entire spectra. Then you have everything after visible light. I call it the danger zone, because you have UV, X-ray, and gamma rays, all of which can give you cancer and kill you. So these are of higher energy radiations. And it makes sense. Higher energy means it can penetrate your skin and has more penetrating power. You can combine these waves to have constructive or destructive interference. If you add waves together that are in phase, meaning their peaks overlap with other peaks, you get constructive interference. And when the waves are out of phase, you get destructive interference, meaning they add up to 0. So from this interference, you can get a diffraction pattern. So if you have interference of two waves that are propagating next to each other, they will combine in a way where it creates constructive and destructive interference in alternating patterns. So you have a light and dark spot if you were to have a film after these waves propagate through two slits. And this is called two-slit interference or two-slit diffraction. You also have an important thing called the photoelectric effect in this chapter. So the photoelectric effect, I will sum it up and listen to this. It's very important. You have light. Light comes in and strikes a metal surface. The light has a certain energy, a certain frequency. So if you have the frequency or even the wavelength, you can calculate the energy of the light. Okay, so you have the light coming in with a certain energy. What does the light do? It hits the metal. It gives enough energy to the metal to release an electron from the metal. Because we know electrons in metal surfaces are just a cloud of electrons that go from atom to atom and they kind of bounce around because metals are conductive, meaning they can conduct electricity, meaning electrons will go up and down the metal surface willy-nilly. But if we were to remove an electron, this requires a certain amount of energy. The light coming in supplies that energy, which we can calculate based on the energy of a photon. So the photon comes in, it has a certain energy, it releases an electron. The energy required to release this electron is a certain value. The remainder of the energy, let's say light comes in with more than enough energy. Some of that energy, let's say one joule is required to remove an electron. The light comes in with 2 joules. What will happen? One of those joules is used to emit the electron. The other joule doesn't just go away. It's used to give the electron kinetic energy. So the light coming in equals the light that is equals the energy that is required to emit the electron and, meaning plus, the energy of the kinetic energy of the electron coming out. This can be represented by an equation, multiple equations. So here is what we have down here. We have E photon, which is the energy of the photon coming in, equals theta, which is the binding energy. So the energy that is required for the electron to escape the metal atom. Binding energy. That's the minimum energy required to knock off the electron. Plus the kinetic energy, meaning the excess energy brought through in the photon that will be translated to kinetic energy or to the speed of the electron coming out. And how do we determine these energies, right? Here's Einstein's equation. So E equals h nu. So h is Planck's constant, 6.626 times 10 to the negative 34 joules times seconds, times the frequency 1 over seconds. And then you get this, the seconds cancel out, and you get joules. Now this energy is in joules, and this is the energy of one photon. You can calculate the energy of a mole of photons by taking this number, multiplying it by Avogadro's number. Or you can do 2 photons or 3 photons, etc. You can then plug in C over lambda for nu to come up with this other version of the equation. But they can both be used. Now, if we plug this equation in for the photon into the photoelectric effect, you have the following. H nu, which is the energy of the incident light, minus the energy required to knock off that one electron, equals the kinetic energy or the remainder of energy that is converted to kinetic energy of the electron. And that's 1/2 mv squared. So that's the photoelectric effect. We also have emission spectra. So emission spectra, basically, in a nutshell, every type of element, when given energy, excites its electrons. When those electrons come back down to ground state, visible light is emitted. This visible light can be detected and is part of a line spectra, right? So it's not continuous. An example of line spectra is when you have neon lamps. Neon lamps have a different concentration or percentages of neon, argon, and krypton in gaseous form, these noble gases. They are excited by a current. This current excites the electrons. When the electrons come back down to ground state, light is emitted. Energy is emitted in the form of visible light that can be pretty colors, and it can light up a neon sign. So there are several emission spectra. There's a different emission spectra for each element. The more complicated the element, meaning the higher the protons and the higher the electron number, the more bands you will have. So helium is a relatively simple element, only having 2 protons and 2 electrons when it's neutral, meaning it will only have a few bands. It may not be 1 electron per band, but it'll be less colors. Barium, which is a larger atom and has more protons and more electrons, it will have more bands. So how do we quantify this? We can quantify the energy that is emitted when those electrons come back from the excited state to the ground state using Bohr's model. And this is going to be given to you. The energy of the photon at a certain energy level is negative 2.178 times 10 to the negative 18 joules times z squared, which is the atomic number of that element, divided by the energy level. And we'll learn about what n equals later on. So n is an integer value, and it is determined by the energy level of the electron. So you can have energy level 1, 2, 3, 4, 5, 6, 7, etc. So here is the example of the Bohr model. Energy comes in, light comes in, it excites these electrons. They are going to a higher energy level. When they come back down, they will release energy in the form of visible light. The more they come back down, meaning let's say energy level 5 to 1, more energy will be released, and the visible light that has the most energy is violet. Violet would come out. If you had n equals 4 to n equals 2, for example, a less energy visible light will come out. If you have n equals 3 to n equals 2, then an even less energy visible light will come out, such as red. And you can calculate the change in energy from going from n equals 5 to n equals 1, or really any energy level, using that equation and just doing E final minus E initial using the Bohr's model equation. And then from there, you can actually use finding that energy. You can solve for the frequency, you can solve for the wavelength, and you can even solve for the color of light that is coming out once the electron goes from n equals 3 down to n equals 2, using the energy, and then going back to the relationship between energy and frequency, and then the relationship between frequency and wavelength. Then we have the de Broglie wave model, basically meaning that every particle, even if it has a mass, can have a wavelength, and this equation can be used to calculate the wavelength. We have the Heisenberg uncertainty principle, basically saying that we cannot determine the position and momentum exactly at the same time of an electron. So there is some uncertainty of position and uncertainty of momentum, which is velocity. So then the last key point of chapter 8 is the quantum numbers. Now the quantum numbers, I like to call them the energy coordinates of electrons in an atom. So the principal quantum number is n, and it can be an integer value from n equals 1 all the way up to, in the periodic table, we talk about energy level 7. That's the highest one we talk about because it relates to the periods. So we have 1 all the way up. And the quantum number L. L represents the subshell. L subshell represents the subshell that the electrons are in. L equals 0 equals S. L equals 1 equals P. L equals 2 D. L equals 3 F. So it goes SPDF. The value of L is defined by a range depending on what n is equal to. For example, if n equals 2, then L could either be 0 or 1. And this range is from 0 to n minus 1. So if you have n equals 4, the possible values for L, 0, 1, 2, and 3. So it is defined by a range determined by n. The magnetic quantum number. It is determined by the value of L. So if L equals 1, the possible values for ML, -1, 0, and plus 1. If L equals 2, -2, -1, 0, +1, +2. This represents the magnetic quantum number, or the three-dimensional orientation of the electrons in space, basically the orbital, whether it is in one of the orbitals or another. So for example, L equals 2 corresponds to D, right? A D subshell has 5 orbitals. So these are represented by these ML values, the 5 positions, -2, -1, 0, 1, and 2. Another example, if we have L equals 1, that corresponds to P. P has 3 orbitals, right? There are 3 p orbitals. And these orbitals are basically positions where electrons can be held. So if we have L equals 1, the possible ML values are -1, 0, and 1. So there's 3 possible values, 3 possible orbitals where the electron can be positioned. Okay. Now, the last quantum number is magnetic spin, or ms, which simply means the electron can spin in one direction or the other direction. And the values can either be +1/2 or -1/2. That's it. So for every ml value, such as, let's say ml equals +1, there can be 2 possible electrons positioned there, one going up, one going down. So from this, we can determine the number of electrons that are possible in each energy level. And it's a good exercise. You can pause the video and try it on your own. So for n equals 2, for example, we have 2 possible L values, 0 and 1. This corresponds to S and P. But if L equals 0, ML can only be 0, meaning there is 1 orbital. Each orbital holds 2 electrons. So there's 2 possible electrons in this S orbital. Still, n equals 2, another possible L value is L equals 1. This corresponds to P. If L equals 1, the possible ML values are -1, 0, and 1. Those are 3 orbitals. So a total of, in the n equals 2 energy level, we have a total of 4 ML values. We have 0, -1, 0, and +1. So there's 4 orbitals, right? 4 orbitals times 2 electrons per orbital, 8 total electrons. So there's 8 possible electrons if the n equals 2 energy level was filled up. Try the same thing for n equals 3 and even n equals 4, and you'll get the point. So here's some questions. You can pause the video and take a look at them. And again, here we go. How many electrons are possible for n equals 3? Pause the video and try this on your own. Then simply we have these orbitals are different shapes. The s orbital is spherical. The L equals 1 or p orbitals have a dumbbell kind of shape like this, or we call it peanut shape, where there are 6 lobes. These 6 lobes correspond to 6 electrons. So the p orbital can have 6 electrons total. The d orbital, which is L equals 2, has 5 orbitals or 10 possible electrons. And they are in these kind of arrangements. The f orbitals, there are 7 of them, meaning a possibility of 14 electrons. So all I would remember is L equals 0, 1, 2, 3, S, P, D, F. S, possible 2 electrons. P, possible 6 electrons. D, possible 10 electrons. And F, possible 14 electrons. And that's it. So if you have any questions, please leave them at the comments, subscribe, and like the video. Thank you so much, and enjoy your day.